Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
Work and energy. We talked about this topic briefly already when we were discussing the vector calculus. If you remember, in that case, we were pulling a box on the floor, and of course there will be a displacement in such a case. So let's say the box moves from here to here. So we had force pulling on it and then some displacement S. And let's make them vectors as well. So in that case, we learned that the work done on the object was defined as the dot product of F, the force, and the displacement. And the dot product, again, just takes into account the component of F parallel to S. That is the horizontal component in this case. There is no work done in the horizontal direction, and that's what the dot product tells us. But this isn't the complete answer. So in this model, we were assuming that the force is constant. Then we could just simply take the cross product or the dot product. But the more general expression of work, so let's put this in parentheses. The more general formulation is that the force can be varying. And in that case, we have integral of F over some infinitesimal displacement S. So instead of having S, we have a ds. So this is ds. And this concept can be illustrated by this graph. So what we have here is force on the vertical axis as a function of displacement. And as we can see, the force varies in some manner. So how do we calculate the work in this case? The work is, as you maybe guessed, is the total area under this curve. Then we can approximate the area by dividing the area in the small steps like this. So in that case, we have this small displacement ds, and the height of the rectangle is in every case f. So basically what we are doing here, we in the end we sum up all these small steps and we basically get the area, and this is what integration is essentially. So we get this integral formula, and what can we do with this? Let's have an example. So if we have a spring attached to the wall like this, and we push the spring in from some initial position, so there is some displacement x. According to Hooke's law, the force that we have to push the spring with is equal to k times x. K is a proportionally constant called the spring constant. And see what this. Let's see what this integration formula says in that case. So we are integrating over some force F, which is now kx, times some small displacement. And let's go from position 1 to position 2. So this becomes x1, x2 integrated over x, so that's half times k x squared, which is half times k x2 squared minus half times k x1 squared. We identify this expression as the spring's potential energy in the end minus the potential energy in the beginning. So essentially we have here the change in the potential energy of the spring. Okay, so we could also do this for a linear movement of a particle, for example. The integration takes a couple more steps, but the result is half times mv2 squared minus half times mv1 squared. And this is, as you know, the change in the kinetic energy of the particle. So what can we take away from this? The work equals, or the work done on the object equals the change in its energy. It can be kinetic, could be a potential, could be electric, like I almost said. But this is the relationship that ties work and energy together. The sign convention is as follows. If we have positive work, this means that the change in object's energy is positive, which means that the object's energy increases. And the other way around, if we have calculated negative work, object's energy decreases. One example of negative work would be a friction. So if we, okay, let's draw it again. So we have a surface and we have a box sliding on the floor. It has some velocity and it has friction work acting this way when the box is moving that way. So the box has some displacement in that direction. Let's say it stops in the displacement s. If you consider these as vectors f and s, because they're pointing in different directions, we see that the dot product becomes negative. So with the negative work, the object's energy decreases, which means that it slows down the box and eventually brings it to rest. The relationship between work and energy, as presented here, is a powerful tool for two reasons. First of all, we don't have time involved at all, so we don't know how quickly the particle accelerated from velocity 1 to velocity 2, or in a lot of cases, not even what path it took to go from position x1 to position 2. And in those cases, this one is a very good alternative to the Newton's second law, F equals ma, where the requirement of knowing acceleration inevitably leads to the requirements of time, velocity, and position. So in many cases we can skip a lot of hurdles easily by applying the work and energy principle.